Hello, everyone. There's a truth that humans discover more laws than we invent. This stems from the very nature of science and the universe itself. Laws such as gravity, geometry, the Pythagorean theorem, biological evolution, electromagnetism, or the conservation of energy, all of them already exist. They are fundamental frameworks governing how nature operates. Through observation, research, and interpretation, humans have gradually gone deeper into the essence of each phenomenon, which in turn led to inventions such as light bulbs, computers, engines, and machines, and so on. By studying natural phenomena on Earth, Isaac Newton discovered the law of universal gravitation. Those formulas turned out to be so effective that they could not only apply to Earth or planets in our solar system, but also to celestial bodies throughout the entire universe. The reason for this is that the universe operates according to consistent principles, and those principles are governed by mathematics. But how can something abstract like mathematics, something that seemingly exists only in our minds, explain the universe so well? In the 19th century, astronomers noticed that the orbit of Uranus had unusual discrepancies compared to theoretical predictions. By 1846, two astronomers, Urbain Le Verrier and John Couch Adams, independently discovered a completely new planet using Newton's formulas. Neptune, located beyond Uranus, was found. This was one of the most convincing demonstrations of using mathematics to uncover natural phenomena. Physicist Eugene Wigner, winner of the 1963 Nobel Prize in Physics for his work on the laws of conservation and symmetry in nuclear interactions, once said that mathematics sometimes shows an unreasonable effectiveness. Pi is an irrational, infinite, non-repeating number. As of 2024, computer scientists have calculated over 105 trillion digits of pi after the decimal point. But why is pi so strange? Why can it go on forever without ever repeating itself? The answer lies in a mysterious structure, the circle, or the sphere. In ancient cultures like Egypt and Babylon, circles and spheres were seen as mysterious shapes, extremely difficult to calculate precisely in terms of area or circumference. Mathematics at the time was still underdeveloped, and most calculations relied on primitive tools like measuring ropes and rulers. Historical evidence shows that between 2000 and 1600 BCE, the Babylonians had already estimated pi to be around 3.125. For ancient Egyptians around 1650 BCE, pi was estimated at approximately 3.16. They derived this number entirely from practical measurements. By the 3rd century BCE, the Greek mathematician Archimedes was said to be the first to apply rigorous mathematical methods to calculate pi. He created a circle by modifying a hexagon, then kept doubling the number of sides, from 6 to 12 to 24 to 48, and finally to 96 sides. This method allowed Archimedes to estimate pi quite accurately as 3.1429. In fact, according to Archimedes' method, the circumference of a circle is essentially the perimeter of a polygon. The more sides the polygon has, the closer the approximation to pi. Mathematically, this method was so effective that more than 1,000 years later, it was still being used by scientists and philosophers. In China, during the 5th century AD, the scientist Zhu Chongzi calculated pi accurately to 6 decimal places using the polygon method. However, the number of sides he used reached 12,288, a massive leap compared to Archimedes' 96-sided polygon. Fast forward to the 1400s, Madhava, an Indian mathematician and astronomer, is believed to be the first to use infinite series to calculate pi. By 1674, Gottfried Leibniz also calculated pi using an infinite series, similar to Madhava's. But this was an independent development, not a continuation. In 1768, Johann Heinrich Lambert used continued fractions to prove that pi is an irrational number, meaning it cannot be expressed as a fraction. This proof was a major milestone, confirming that pi has an infinite, non-repeating decimal expansion, and that calculating its exact value is virtually impossible. In 1873, William Shanks manually calculated 707 digits of pi after the decimal point, but made a mistake at the 528th digit. In 1882, Ferdinand von Lindemann proved that pi is a transcendental number, meaning it is not the root of any algebraic equation. Then came the era of modern computers. In 1949, the ENIAC computer calculated 2,037 digits of pi. Since then, as computing technology has grown increasingly advanced and sophisticated, we've continued to push the boundary of known digits. The record of 105 trillion digits in 2024 is unlikely to remain unbroken. Throughout the course of human history, calculating the value of the circle has always gone hand in hand with the pursuit of a more accurate value of pi. The circle and the sphere are extremely common structures in the universe. They may seem simple, but in reality, they contain a profound mystery. If someone asks why circular shapes are so mysterious, the answer is perfect circles or spheres don't actually exist in the universe. In mathematics, a circle is defined as the set of all points in a plane that are equidistant from a central point. A sphere is similar, but instead of existing in a plane, it exists in three-dimensional space. According to this definition, circles and spheres are perfect and ideal structures, meaning they can only be perfect in mathematics. Physically, perfect circles or spheres do not exist in the universe. Planets, stars, black holes, none of them are perfect. Even the roundest man-made sphere on Earth, made of pure silicon and weighing 1 kilogram, is not an exception. It was engineered and verified by international standard laboratories. Its surface was polished with extremely high precision, with deviation of only 0.3 nanometers from a perfect sphere. Yet even if the sphere were adjusted so perfectly that there were absolutely zero surface deviation, it still wouldn't be a perfect sphere. Why? Because matter itself is inherently imperfect. Atoms and molecules, when bonded together, do not create a perfectly flat surface. On a microscopic level, matter is rough, fragmented, and non-uniform. Even in the unimaginable scenario, where you could arrange all atoms in a perfectly even structure, the sphere would still be imperfect. That's because on the quantum level, particles are constantly moving. Electrons constantly jump between energy levels. Fundamentally, they are never truly at rest. For all these reasons, a perfectly round or spherical structure simply doesn't exist in the physical world. So, is this why pi is an infinite number? The answer is no. Pi is a mathematical value. It is an irrational, infinite, and non-repeating number. The infinite nature of pi means that any calculation involving it will never be 100% accurate. In other words, calculations involving circles or spheres will never yield a completely exact result because pi itself is inherently imperfect. So, what's the real reason that pi is an infinite number? Why doesn't it ever terminate? In flat space, a type of ideal space with no curvature, where classical geometric rules apply with absolute precision and no error, a circle exists as an ideal structure. It is represented by a continuous line, where every point on the curve is precisely equidistant from a central point, the radius. In this case, pi appears as a constant, defining the ratio between the circumference and the diameter of that ideal circle. Once pi is defined as a constant, it never changes. No matter how large or small the circle, no matter the length of its diameter. In reality, we don't know why pi isn't a rational number. In mathematics, it just is that way. According to quantum theory, everything in the universe is fundamentally discrete. There's no true continuity or seamless structure. However, a circle is created from a continuous line, a series of points in perfect, uninterrupted symmetry. This shows that from different perspectives, mathematics, physics, and reality, contradictions naturally emerge. Perhaps the true nature of the universe is governed by laws so precise that they exceed the capabilities of finite representations, and maybe only mathematics can truly express that level of perfection. Meanwhile, in the physical world, every concept of perfection is merely an idealization. This brings us to another question. If pi has an infinite number of digits after the decimal, how many digits do we actually need in real calculations to maintain accuracy? The answer is not many. In most everyday calculations, using just 10 digits after the decimal is more than accurate enough. For large-scale calculations, like measuring the circumference of the Earth, 15 digits is all you need, and the margin of error is only about the size of an atom's diameter. Even when calculating the circumference of the observable universe, you only need 40 digits of pi, and the resulting error would be about the diameter of a hydrogen atom. Beyond the strangeness of pi, there are other numbers just as peculiar, such as phi, which represents the golden ratio in both nature and mathematics. Just like pi, the golden ratio is also a constant, an irrational, infinite, and non-repeating number, approximately equal to 1.618033 and so on. The biggest difference between the two is that pi only represents values related to circles or spheres, whereas the golden ratio appears in nearly every structure in nature and the universe. Around 2600 BCE, the ancient Egyptians were believed to have used the golden ratio in the design of the pyramids. The ratio between the height and the base of the pyramid is approximately 1.618. Although there's no documentation proving that the Egyptians truly understood the golden ratio, it's difficult to argue that such a ratio was merely a coincidence. During ancient Greek times, many believed that mathematicians and philosophers from the Pythagorean school recognized the golden ratio in their studies. However, this also lacks definitive proof. The name phi, the symbol for the golden ratio, was later attributed to a Greek sculptor and painter who lived in the 5th century BCE. It is believed that his sculptures achieved aesthetic harmony by applying the golden ratio. But to be honest, we also don't have conclusive evidence for this either. More than 100 years later, a mathematician was believed to be the first to describe the golden ratio mathematically. Though he didn't call it the golden ratio, he referred to it as the division of a line segment in an extremely mean and proportional way. By the early 13th century, the Italian mathematician Fibonacci introduced a sequence built on the principle that each number is the sum of the two preceding numbers. Today, we call it the Fibonacci sequence, a numerical form of the golden ratio. By the 15th and 16th centuries, the golden ratio had become a standard in the artistic and architectural style of Leonardo da Vinci. From then until now, beyond its study and development in fields like mathematics, art, and architecture, we've recognized that the golden ratio appears almost everywhere, in both nature and the universe. For example, the spiral shape of a nautilus shell closely aligns with the spiral arms of the Milky Way, as well as many other galaxies across the universe. In nature, the arrangement of leaves on a stem is precisely optimized at an angle of 137.5 degrees. This is a result of the golden ratio. That's because if you divide a full circle, 360, by the square of phi, the result is 137.5 degrees. As leaves grow around the stem, each new leaf is positioned 137.5 degrees from the one before it. This optimizes spatial distribution and sunlight exposure, helping the plant perform photosynthesis more efficiently. Regarding the Fibonacci sequence, if you observe a sunflower, the number of spirals going clockwise and counterclockwise are often 34 to 55 or 55 to 89. These numbers match the Fibonacci sequence. If you divide the latter number by the former, the ratio approximates 1.618. The angle between adjacent seeds is also 137.5 degrees. This arrangement ensures optimal space usage on a limited surface area, and similar patterns are also found in other fruits, such as pine cones, pineapples, and so on. In art, architecture, or mathematics, the golden ratio may be an intentional design principle. But in nature, the golden ratio is an inherent rule. We cannot say that plants deliberately create this. Rather, it's simply part of nature's essence, containing deeply profound mathematical logic. When it comes to life, DNA is the most fundamental structure, and it is, to some extent, also formed according to the golden ratio. In 2016, a research group at Temple University in the United States used atomic force microscopy to measure the physical parameters of DNA. The results showed that the length of one full helical turn is approximately 34 units, while the width is approximately 21. This ratio also comes out to about 1.618, which closely aligns with the golden ratio. As for the twist angle between successive base pairs, it's about 137.4 degrees, also roughly matching the golden angle. Of course, this study has received mixed reviews. Some argue that this is merely an overstatement of the golden ratio's role. The 137.4-degree twist angle is a value that has not been widely verified, although the length-to-width ratio has been confirmed by numerous earlier studies as accurate. So at the very least, we can see a glimpse of the golden ratio appearing somewhere within the structure of DNA, one of the most fundamental forms of life. If you don't believe in these things, then you might simply consider it a coincidence. On the other hand, you might view it as an expression of the golden ratio itself. What we know about nature is still very limited, but we also can't deny that the golden ratio is truly a principle embedded in the fabric of the universe. Returning to the question posed at the beginning of the video, why is mathematics so effective at describing the universe? Is mathematics a fundamental law of nature, or just abstract principles created by the human mind? From the examples above, it's clear that mathematics has always been part of nature's rules. Yet humans have developed it to such a sophisticated level that only a small portion of the world's population can truly grasp it. To be honest, I myself don't fully understand it either, but I can feel its wonder. Aside from pi, which represents the ratio of a circle, or phi, which represents the golden ratio, nature still contains many other fundamental constants. For example, the gravitational constant, Planck's constant, the speed of light, the fine structure constant, Avogadro's constant, and so on. Einstein once said that at some level, pure mathematics, with its certainty, seems to transcend the reality we can observe, and that truly is a mystery. The goal of physics is to use mathematics to make the universe more comprehensible, and that is an extremely difficult challenge. Einstein spent much of his life pursuing what he called a theory of everything, and many physicists today still aspire to the same goal. However, Gödel's incompleteness theorem suggests that such a theory may be nearly impossible, because mathematics contains deeply inherent contradictions that even humans don't fully understand. As for quantum physics, the deeper we go, the more complex it becomes. This complexity is sometimes so immense that it exceeds the processing capabilities of the human brain. Regarding the question of why mathematics is so unreasonably effective, the only possible answer is this: the universe is not just something that can be described by mathematics. The universe itself is a deeply mathematical structure, a kind of source code that governs the operation of all things. When we look at our everyday lives, mathematics dominates every field. From inventions and machines to weather forecasting and spacecraft, all of it is the result of mathematical formulas distilled through thousands of years of human history. Music contains mathematics, life contains mathematics, and the infinity of the universe, that too is mathematics. This fact is so obvious that we can't even comprehend why mathematics is so effective to such an unreasonable degree. In the end, this video, just like the previous one about infinity, covers topics that are outside my area of expertise. They're abstract and deeply profound, which makes the reasoning and examples sometimes incomplete or not entirely satisfying. If you have any suggestions, feel free to leave them in the comment section.